Uh, MR came around, MRI came around about 82, I think, or early 80s. I read an article about it in Scientific American in, I think, 81, 82. And it took off pretty darn quickly, mostly because you could diagnose multiple sclerosis with MRI of the brain right away, and there was no other way to do it. So it got FDA approval and everything super record time. And it grew out of university. So it has a really cool, essentially, ethos of academia plus industry. And most of the IP for MRI came out of academia in the first 15 years. And there's a lot of really cool little inventions that improves MRI. And so it's a great field to be in. For young people, I would absolutely recommend the society that runs the major meeting. About 6,000 people a year show up to the meeting, so it's a really vibrant community. Okay, so we're getting pretty familiar with this configuration where you have a tube, right? Whether it's a PET scanner, a CT scanner, and there's a patient table that is controlled to within fractions of a millimeter. You can move the patient inside the tube. And the difference here is the patient is lying on top of a set of essentially roughly circular copper tube. And those are receiver coils, and there's a set of receiver coils placed on top of the patient. And these receiver coils are going to measure RF energy that is coming out of the patient in the range of radio frequency. And which is kind of weird when you think about it. Like, how are you going to make medical images that have a resolution that are sub-millimeter of radio wave, right? As opposed to the photons that are going through in CT, are scattering and getting resolution because of the photons. In MRI, we're using radio waves, which have wavelengths of a meter or a fraction of a meter. So for cardiac MR, you have a couple of additional things, the same as we saw with CT. You have a set of ECG leads that are put on the patient, and then basically the 3-lead ECG comes out with tracing of the scanner, as well as monitoring the state of the patient. In cardiac, you want to know how they're doing, the heart rate rising or still stable. And then also we have that same injector that had to be modified somewhat for MR, such that it didn't give off radio frequency noise because it's inside the room. And it also doesn't have ferromagnetic parts because this is a very large magnetic field here, and you don't want large objects getting sucked into the scan because they're ferromagnetic. So this patient is lying on top of a coil. There's probably a coil under this dressing here, and has some ECG leads on. Also notice this patient is wearing ear protection, and you need to cover the patient's ears or put earplugs in, because inside the scanner, when the MR is going on and you're switching the gradients, the noise can get up over 100 decibels, so you can actually get some sort of stress on your hearing. And they worked a lot at trying to make them quieter, but there's only thing you can do to make them quieter. But when the thing's working well, it produces amazing pictures. So here we have a movie. Once again, OSX and PowerPoint are not, doing well with each other. Let's see if we can get out of here and just put it into this space. There we go. So here we've essentially have an EKG for this patient. We gate our MR acquisition such that it's in phase with the heartbeat of the patient. Oftentimes we need about on the order of 10 heartbeats to make a really nice movie of a single slice of the heart. you can see there's really tremendous contrast between the blood pool and the myocardium. This is the muscle here. This is the right ventricle. Blood pool is bright, myocardium. You can see there's some kind of coherent signal that's flowing around in the blood. This is the patient's liver. This is all interstitial fat. This bright stuff here, this is fat just under the skin. Chest wall of the patient is here. This is the patient's left lung. And the great thing is you get this dynamic understanding of the motion immediately, right? So it's like echo in that the static pictures look okay, but when you see the movie, it's even better in terms of understanding how the heart's doing. Up here, remember in CT we had those white circular dots here that were the coronary artery piercing the imaging plane. Here you have that, there's a pad of fat, which is the bright signal, and then these little circles here are the arteries that are running through that slice, and there's some arteries down here as well. And I think that's pretty well most of the features we see there. If we go to the next movie, which is the slice we were just looking at is orthogonal to this. So if I draw a line through here, I would have seen the short axis slice with the left ventricle and the right ventricle. Now, this scan plane, we have intersected the apex of the heart and the two atria and the two ventricles. So this is the classic 4-chamber view that we saw with echo, and then we saw with CT, and now we're seeing with MR. The difference with MR is you actually collect it in this orientation. You have to select the orientation on the controls of the scanner, and you, instead of collecting 3D and then reformatting it this way, you actually collect the data in this plane. And so that requires a skilled technician to actually program into the scanner what the orientation of the plane is to collect this appropriate plane. A lot of that, the manufacturers are working hard on automating all of that with AI, basically. So you just take a scout scan, and then the scanner will just say, I can give you a 4-chamber view, and it just does it, right? As opposed to the tech having to figure out what landmarks to use, etc. But here again, we see some very interesting coherent signal that is obviously proportional to the blood flow in the left atrium in this case. We see nice dynamic information about the mitral valve leaflets and how they're coapting or coming together and then bouncing open at different phases. We see the valve between the right atrium and right ventricle. This is the right coronary artery that is bouncing up and down here, as we've seen on TV. And we also see the descending aorta. Again, there's some kind of coherent swirling that you can appreciate there. As we'll see when we study how to encode information from MR, if this blood flow was not absolutely reproducible over the course of 12 seconds, so 12 heartbeats, we'll say, right? So 12 heartbeats went into making this movie. If this flow was completely random, it would not be encoded like this. You would not see a swirling. It would just look like random signal going up and down the whole field of view through the motion artifacts. So what that tells you is the flow inside these chambers is pretty darn reproducible, right? From beat to beat, it does this kind of swirling. And you can imagine designing some kind of AI signal processing methodology by which you actually measure the blood flow from these gradients that are flowing around in the chamber. And you could validate it with, as we'll see, phase encoded blood flow. Because if you have the time and the patience, you can actually get a vector field for all of the motion that's going on in this movie. And you can directly measure it with MR using the phase of the signal. We'll see that when we look at applications. Here's the classic orthogonal view to that one. This is the 2-chamber view where we have the left ventricle. We see very robust contraction or robust left ventricular function. The left atrium, nice mitral valve dynamics shown here. We also see the descending aorta here. This is the ascending aorta here. That large circular thing right there, whose flow is kind of out of phase, that is the great cardiac vein. So that's blood coming back into the heart, or back into the, I should say, the right atrium of the heart from the muscle in the heart. So as the blood is draining back from the muscle in the heart, it accumulates in this large cardiac vein and goes to the right heart. The venous flow in the heart. And this big old tube here provides actually a pretty nice transport roadway. If you have a catheter and you want to get something somewhere, putting the catheter down this vein, you can actually travel onto the lateral wall of the heart and places like that to do that. So that's used quite a bit. Again, this signal here is fat, shows up bright. The sequence that's been used to make this movie. There's something really bright here. I'm not sure what that is, whether that's blood. And then the reason this blood is bright, you can see the blood that's flowing in to our imaging plane is brighter. We'll look at the mechanism by which that occurs. So blood that's out of plane and then flows into the plane for many pulse sequences looks quite bright, because the magnetization hasn't really been touched by radio frequency pulses yet. And so they're new to the elicitation of signal from them, and they give off a lot when they enter the plane. So you get an appreciation of inflow that way. If anyone has any questions about what's going on in this, I'm happy to stop and try and figure it out. The other thing we can do with magnetic resonance, let's go back here. With this type of imaging, this is called spin echo imaging, and we see there's dark signal now in the ventricle where there's blood. We'll look at that mechanism as well. This is a very old image, actually, that I took when I first got to Hopkins in the late 80s. So this is a long time ago, really, 35 years ago. And this is a 22-year-old graduate student. Normal myocardium, nice. He was a very athletic person, large chambers, lots of good motion, etc. So this is end diastole, when the left ventricle and the right ventricle are maximally dilated and full of the most blood that's going to go into them, right, in the resting state. And then this is when the chamber is at its smallest. And so that's end systole. So you can calculate ejection fraction, as we know, by looking at how much blood is different from here to here, and then normalizing it to what you started from. That's the ejection fraction. That's easy to do. But what we can also appreciate here is, like, if you look at basically this looks like 8 millimeters or something, or 10 millimeters across here. And then at end systole, when the muscle's contracted as much as it can, it's punched up as much as it can, that obviously gets thicker, right? And so you can measure how it changes its thickness over the course of the heartbeat by getting off a series of pictures like this. And so this would give you myocardial strain. And myocardial strain, as we saw, you can take the starting length, right? Take the difference between the starting length and the ending length, normalize it to the starting length, and get a fraction of strain. Really get a nice estimate of strain in the right ventricular wall here. Now, you can appreciate it when you just look at it quickly and you squint, especially, and you go, oh man, I can see that it got thicker. You then go in here and actually try to reproducibly measure this thickness. It's a little tricky, right? Because there's a soft edge here. It's like, well, where do I put the edge? If you ask 10 people to do it, they're going to put it plus or minus 2 millimeters along there. And so what you can do with MR, which is really unique, is you can use radio frequency energy and gradients ahead of making your image to actually saturate out signal in very selected locations. And so in this case, before we started taking any images, we played a radio frequency pulse coupled with gradients to actually saturate the signal from parallel planes through this patient. And then we went to make the image of this short axis plane, the intersection of those parallel planes that have been saturated, and our imaging plane produces these lines, right? So the tissue at this point is entirely and fiducially marked by this saturated signal, right? So if it moves, this line is moving with it, right? The tissue is, this has been stuck onto the tissue. It lasts, as we'll see, proportional to T1. So this contrast between this stripe pattern and the background fades away over time. However, as luck would have it, T1 is long enough that it lasts at least from end diastole to end systole. And you can then actually really accurately measure what is the strain in this direction. So if I'm looking along perpendicular to these stripes here and ask, well, the muscle actually, when it shortens, is shortening in this circumferential hoop direction. So all the muscle just essentially pulls that hoop in. And the distance, if I measure the distance around here, call that circumference 1, difference around here, circumference 2, it's going to be shorter, right? And that amount of circumferential shortening is also a strain. With this technique, you can measure that circumferential shortening extremely locally. So if I just look at the distance between these two lines and measure it and say, okay, that's 7 millimeters. And then I come across here and I find the same two lines and say, well, now the distance is 4 millimeters. I can get a very accurate estimate of the strain in this very small section of the heart, right? So this is essentially the myocardial strain in human hearts. And you should put these lines on it and measure the distance between the lines. It will give you the most precise estimate of myocardial strain. And in this volunteer, because they're so healthy, you can see the right ventricular wall also has been tagged with these things. These are called myocardial tags. And then we can measure their distance here to get strain in the right ventricular chamber on the free wall of the right ventricle. And I think we have to pop out of here once more. Yeah, this is a movie. You can see the evolution of that strain over the course of systole. So this movie goes from end diastole down to end systole, and then we don't take any more data, it just pops back to end diastole. Okay. We'll see other examples of this, but you can see you have great strain values, plus you have temporal dynamics of the strain. So if the temporal dynamics of the strain on the septum over here was different than that we see on the free wall, it's absolutely obvious that you can measure it with great precision using a technique like this. So this is called myocardial tagging. Big deal for cardiac imaging for a while. And this is what it looks like when you do, you really focus on trying to make high resolution myocardial tags, and you do the vertical and horizontal direction. I'm going to jump out of here to make the movie go better. There we go. Get vertical or tags and horizontal tags. So you have to take them separately and combine them later to make them optimal. But now you have little squares, you know, that are like 3 by 3 millimeters. And the deformation of that square, oops, sorry, go back to the movie. What happened there? See if I can zoom it up. So the deformation of each one of those little squares, it starts out as a nice square box, and then it deforms into some kind of, you know, parallelogram or some kind of, you know, tetroid thing. And so you have the two-dimensional strain of that little square box by the end of it. That's pretty cool. So that, you know, if this person had, this is the person. So the way this data was obtained was, it's probably in a porcine model of ischemia or something, but this is all normal strain here. But the ventilator and the ECG were both used in gating. So we gated to the ECG, or every heartbeat, plus we phased it with how the ventilator was operating. So you got this extremely high resolution data. Hard to match this data in humans or get this in humans. Okay. Now the other thing you can do, so that's myocardial tagging, and that's a way to look at myocardial function with high temporal, high spatial resolution in hearts that are reproducibly producing the same strength. There's another thing you can do, and that's make a vector field of the velocities of the, say we take a voxel, 3D voxel, it's say 5 by 5 by 5 millimeters inside the patient. We can measure the velocity of that box and how that velocity changes over the course of the heartbeat. And I think I brought this up. Yes, I did. Here we go. Okay, so this these are MR images. Let's go back and run through this slowly. The brightness here is, in fact, this is a single slice through a lot of great vessels here, right? And in that slice, what we have marked as signal is the phase of the signal that's coming from each voxel. And we'll look at this in detail mathematically. And you can make that phase represent the actual velocity of the blood in that voxel. And so this bright signal could be blood that's coming towards us. 0 is our pixels that aren't going either in or out of the plane. They're just staying in the plane. So this is 0. And then the negative ones are the ones that are into the plane. And you can measure that phase shift at different times through the heart cycle and play that back, and you get a movie of how those phases change over the heart cycle. Then what you can do is say, now I have a velocity field, and this is going through a 3D velocity field and looking at different pixels. Now what I can do is with that 3D velocity field, I will, at a certain time, I'll put a set of particles, I'll just lay them into the volume, and then I will let the velocity field drive the particles on a trajectory, right? And it's amazing what you get, right? So this is like I just drop some, rice in there, and then woof, out it comes with all these different velocity trajectories. And so then this is the full 3D map of this person's velocity field out of their aorta, inside their ventricle, in the right ventricle, up the PD cava, stuff like that. And so for doing pre-surgical planning for how you're going to treat some congenital abnormality, for instance, this is fantastic. You can see where the blood is going through what chambers and through what orifices, right? And so this is called 4D phase contrast imaging, or 4D flow. There's somebody here, Albert Schau is one of the world experts in getting this to work on a scanner in people, and he does many of these cases each week here. So that's another MRI, is you can measure directly motor velocity. So let's take a look at some of the fundamental technology / physics that's going on here. And this is just a cartoon of an MRI scanner, and it's a pretty old cartoon because the magnet itself is enormous. Okay, so it's, as you can see, the magnet is almost the same length as the person. So this really only occurs nowadays if you have like a 7 Tesla magnet or some very large magnetic field. Normally, 90% of the MRI systems sold are between 3 Tesla systems and 1.5 Tesla systems. And what is a Tesla? It's the strength of the magnetic field that this person is bathed in. And that is created by current in windings that are going around this patient in a cylindrical way. So those current windings there's, a lot of wire inside this cassette that has these windings in here. And what you do is you fill this chamber here, plug it in, and you pour in liquid helium, right? And so all of these wires are essentially bathed in liquid helium. So you make the wire out of a material such that at the temperature of liquid helium, below 2.7 degrees Kelvin or whatever it is, that wire becomes superconducting. And so there is no resistance to running electricity in those wires anymore. And so you can essentially ramp up the current slowly in these wires. Once they're cooled down, you put, there's a thing here where you put your voltage source across two poles, and you just slowly ramp the current up in that loop, in that connected loop. And then once you're at a level that magnet is rated to work at, so its max could be 1.5 T or 3 T. Once you get to that level, you then flip a switch, and then the current is totally self-contained inside that helium compartment in those wires. You take off your source. And that magnetic field, which is going this way, is pointing out of the scanner and then wrapping around and then going back into the scanner that way. Those are the field lines. We'll come out here, wrap around, come back around. In the middle here, you have the peak field, and it's on all the time. Right? So when you go home at night, you don't flip a switch and the magnetic field ramps down. It stays on the entire time. It's quite a dramatic thing when you get what's called a quench, which means that the superconducting aspect of the wire is lost, and then a lot of resistance enters the system, and all of that energy that's stored in the current comes out in a pretty rapid fashion, and you boil off a lot of helium really quickly, because as it all heats up, the helium goes to gas, and it creates an enormous pressure in here. So you need a pressure release valve up here that the helium gas then vents out of the room. You don't want to fill the room with helium gas, right? People will asphyxiate, and they will asphyxiate in a comical way because they'll be yelling at each other. Get out now. And so that's called a quench. It's not that dangerous because the helium's venting out of the room. You can online, if you type in MRI quench, there'll be videos of people who purposefully quench magnets out in the field or whatever, and try and measure the energy and everything that comes out of there and how to cope with that. So it's relatively safe. However, there is an emergency stop button on the wall in the scanner room, okay? And if there is a crisis, and that crisis is, for example, a tech is standing here and somebody rolled an oxygen can or oxygen bottle and it slams up against the side of the magnet with great force, and the tech can't move because they're trapped and they can't breathe, right? Then there's a big red button on the wall. You hit that button and it will quench. It will actively quench the magnet and try and ramp down the field. It's possible, it's safe. However, you don't want to hit that when you don't need to hit it, because it costs about $50,000 or something to come in, fix the magnet, and ramp it up. So but for an emergency, you do need that quench button, because the major essentially hazard of MRI is flying metallic objects. Right? Because when you walk into this room, and if this is a 3 Tesla scanner, and if I had a standard hammer and I was just standing right here, and in my hand I had just the hammer I took out of my toolbox, right? I could not hold on to that hammer. It would be absolutely impossible to hold on to it. And once you feel it, I've been here, seen it happen. Once you feel it move towards the kicks in, it's too late, right? Because it gets closer and closer, gets stronger and stronger, and you cannot hold on to that thing, and you're kind of a fool to try and hold on to it. So it goes. And then if there's somebody laying in there, it flies in, it can do a lot of damage. So most of the fatalities associated with MR, there's probably like 10 or on the order of 10 people getting hit by metal objects that are flying, or people getting pinned to the side of the magnet and they can't breathe. Things that have gone in are all those floor polishers that have a big rotating bottom or pad, and so the janitorial staff like cleans the floor with those things. Seen a couple of pieces of those in there. My boss at Hopkins put one in a magnet. And so at that point, like when you've got a very large metallic object sitting here and stuck, usually on the back wall, there will be a large bolt on the wall with big eye bolts. And for things that you can pull out, you'll just attach it with straps and just crank it out, right? And there'll be a moment where it's floating in space right here. It'll be an office chair or a floor cleaner. Again, just floating there as you're pulling it away from the magnet. And you hope that you're not jiggling these conductors around to cause a clinch. Like that. So that's why there's all these warnings outside the room. They used to, when I first started this in the 80s, they had metal detectors like you have at the airport. And each door had a metal detector. And so when you walked in, you had metal, it would buzz. And this was a great example of when false positive calls ruin in technology. So if you walked in with eyelets on your shoes that were metal, the dang thing would go off, right? And so virtually 50% of people, the thing was going off. And so people just stopped using them. They'd shut them off, right? And so they aren't used much anymore, like the MR scanner. Usually there's a big warning on the door, usually a set of shelves right at the door. Take your wallet out, put it on the shelf, because you're going to erase every credit card you have, right? And you take your ID because it's got a magnet, put that there. Get all of your penknife. Okay, around or inside the radio frequency or the main magnetic field coils are another set of coils called gradient coils, and inside that is a radio frequency. So all of these things have current running in them, and that's how we're going to run this scanner. Any questions about MR setup here? There are other ways you can do this other than a huge, superconducting magnet, but this is basically 99% of MRIs done this way. Interestingly, the guy I did my PhD with in Toronto, he was early in technology. He used to do pi meson therapy with a particle accelerator in a place called Triumph in British Columbia. That was his health physics thing. And then when MR was first proposed, a lot of our first came out with MR, this guy that I did PhD with, Mark Henkelman, sat down and tried to figure out how this would scale up to humans. Like, could it scale up to humans? And so he worked out that, yeah, you could do it, but you would have magnets the size of pickup trucks and they would cost millions of dollars. So that's not going to happen. And now here we are. We got magnets the size of pickup trucks, and they pay it. They're cost millions of dollars. So anyway, very quickly you got into it. So here's a standard clinical unit. This is a picture of the one here at UCSD. It's 3 Tesla magnet. This is from many years ago, like now 9 years ago. So you can see the bore here. This one looks like it's only about 55 centimeters, something like that. Here's what a 7T unit looks like, and then here's 3 experimental units that were put into research labs that are much higher fields, like 9. Here's a 12 and a 12 Tesla unit. So you see the relative size of the person compared to this thing. This is one in France a long time ago, actually. That's why it's so huge. And so the reason you drive up to these higher and higher magnetic fields is because the amplitude of the signal you measure just is proportional to this, right? The frequency goes up and the sensitivity of you receiving signal from the patient goes up with main strength. So you can make pictures with smaller voxels, right? You don't need as many protons, and so you can make high resolution pictures. But the field itself is really high. Like a 1 Tesla field is 10,000 Gauss. And if you talked about magnetic fields in elementary school or high school, when you kind of magnet, compass, and all that, the Earth's field is a half a Gauss. Okay, we're all bathed in a magnetic field. It's a constant magnetic field on our lifetime scale, and it's a half a Gauss. These fields that we're using are like 10,000 Gauss, right, or and upwards. So much bigger. The fundamental occurring is that for most of what we're going to image, most of it imaging protons. Protons are that comes back from the patient, and again, with those protons will absorb radio frequency energy and then re-emit radio frequency energy. That frequency is governed by the magnitude of the static magnetic field. Okay, each nucleus that has an odd spin will experience nuclear magnetic resonance, and each nucleus has its own coefficient that maps the frequency to the magnetic field. So carbon and phosphorus and nitrogen or fluorine, things like that, have different gamma values. So they will resonate at different frequencies for a specific field strength. So at 1.5 Tesla, which is like 80% of systems, the Larmor frequency for protons is 64 megahertz. Okay, so we're going to make an RF coil that radiates the patient with 64 megahertz. Our receiver coils will be tuned to listen for radio frequency emissions from the patient that will be at 64 megahertz. That's called the Larmor frequency, or the resonance frequency. And for those of you who still use a FM radio in your car or whatever, KPBS is at 89.5 megahertz. So it's all the way on the left side at the low end of the radio frequency spectrum for FM radio. And so we're off down below the dial, right? But the fact that this frequency is used and higher, right, so 102 megahertz and stuff like that, tells you that we are bathed in radio frequency energy that is very correlated as well as background noise, right? And so one of the things we have to do with magnetic resonance imaging is we have to place the system inside a room that has been absolutely RF shielded. So that means when you close all the doors of that room, the door actually has tongues on the side. So it's sealed shut. Sealed not in an airtight way, but in a RF type way. So when you get in there, it's truly a silent room, right? And so you can communicate however you want between your phones. Nobody's going to hear it outside, right? Because no radio frequency energy gets it. And no radio frequency energy that is bathing us right now is into that room. So it's a silent room. That makes it kind of an expensive construction project. So you don't just have a room, you have to have some super specialist RF shielding company come in and make a box, a Faraday cage box for you to be inside the room. If any signal goes in and out of that box, it has to go through a patch panel in which the cables that are going into the room go through the patch panel. And those cables usually have a filter on them such that it filters out any noise that's going to go in. Or you can put it through an optical fiber through a long tube that is a natural filter. So you can have a really long hollow tube of copper, and it's kind of a natural filter for signal that's going through. That's about it for radio frequency. Okay, so here is, again, just to refresh our memory, the patient's going to go inside this tube. They have strapped upon them these coils that are radio frequency antennas, essentially. And they're called coils as opposed to antennas because an antenna theory, when you look at it in electrical engineering, usually you're assuming there's a plane wave coming from infinity that you're going to receive. Here, these are our source, not a faraway source such that we get a plane wave. Our source is right underneath the antenna. And so these are rarely called antenna, they're called coils. So you have a loop of wire, you put it over the patient, and inside that loop, you induce an oscillating current that is at 64 megahertz for this 1.5 Tesla system. And we're going to measure that as our signal. So these are receiver coils, they're called. Nobody ever calls them receiver antennas. This device, recall, is the one that is inside, farthest inside. So we had a set of coils providing main magnetic field. We have another set of coils, which we call gradient coils, which we'll look at next. Inside that is this, these little lines here. This is a radio frequency transmitter. That's what we're going to use to bathe the patient in radio frequency energy. And so this is what the radio frequency transmitter looks like, cartoon view. And the current is going to flow in these elements in this direction, right? And then come out, circle on here. So you can imagine if I have a current flowing this way on this element, and I have a current flowing this way on that element, I can use my right-hand rule and look at the current path there and go around the direction that that current is flowing, and I'm going to make a magnetic field in the direction of my thumb, right, when that current's flowing. So if I have current flowing down there, like up here, then those two current pathways will produce a magnetic field that's pointing down. If at the same time I reduce the current inside this element and this element, I reduce them down to 0, then I won't have any magnetic field really in this direction. I'll just have magnetic field pointing down, right? So what we do is we take that configuration of a downward pointing field by this, current here, and we change the current in those elements such that the whole thing rotates. So then I'll lower this current, raise this one, lower this, raise the one that's down here, and now the magnetic field it's going in a different direction, right? If I rotate that pattern of current and I rotate it around at 64 megahertz, I create a magnetic field inside this volume, and then therefore inside our patient, that is like a magnetic vector that is rotating at 64 megahertz, right? And that is essentially an RF pulse, a radio frequency pulse at 64 megahertz. That's like a linearly polarized RF pulse that's rotating at 64 megahertz. So when you look at the intensity of the radio frequency energy that the patient is absorbing when we do this, here's the heat map for that intensity. So what's inside the coil gets watts of energy transmitted into it, okay? We have limitations on how much radio frequency energy we can use for this imaging process, in that if we put too many watts into that patient, we will heat them up, right? And so a large patient will heat up more, right? So what you find is that some patients, if you do an MR imaging protocol that involves a lot of radio frequency pulses, we'll see this later. So there's a lot of high amplitude radio frequency pulses used to make the picture. If the patient's really big, when they come out, they're kind of pink. You know, they're a little hot. They're not, it's not like they've been burned by the radiation, but they've just absorbed energy, right? It's not ionizing radiation. All it does. However, there is a terrible thing that can happen is if there's a wire or something, there's a loop on the patient, and it's a closed loop, or even an open wire of just the right length. This radio frequency pulse that you're bathing this patient can generate a current in that wire. And if it's a current and there's a resistance, you get heat and you can burn somebody, right? So if I put on electrode leads, you know, ECG leads, and then the patient lies down and there's a loop in the ECG cable underneath, then when you're irradiating the patient, that loop can start to heat up. And it will heat up enough to burn somebody. And so I've seen that happen as well. And so that's another hazard. It's just burning a patient through inducing current. These elements here, we induce current in those elements, obviously, but when we're transmitting with this, you know, large amplitude radio frequency pulse, these are designed to measure very small amplitude radiation from the patient. You usually actively block the resonance of those elements while you're transmitting. So you'll put some kind of bias, DC bias current into the circuits that takes them out of resonance. So they no longer they are listening when this thing is transmitting. And then after you've finished your transmission pulse, you will change the voltage on that bias such that you can turn the coil on, and they will listen for a much smaller signal for the patient, like many orders of magnitude. I don't know what it is, like 5, 10 orders of magnitude smaller signal. Right? Those are called receiver coils. Receiver coils can start looking pretty crazy. This is one of my favorite slides that I got from a colleague at Brigham and Women's Hospital. And this is when they had home-built radio frequency coils for the brain that had many elements. And so each one of these loops here is a single elemental coil that is attached to a preamplifier and will, you know, sample the signal that's coming from the patient right underneath the coils. It doesn't really get much signal from over here in the patient, just right underneath. This coil back here gets the signal underneath the patient here. And so you have the summation of very small volumes with many small volumes. And the reason you want to do that is because most of the noise amplitude comes from the patient. So you don't really want to gather up noise from the whole patient. You would like signal and noise from an isolated volume, and then we'll add all that stuff up to make a final picture. This is a 32-channel coil in the head. Each receiver is tuned to be on resonance. Again, they're switchable, such that during transmission, they're not on resonance. And when you overlap them like this, there's a clever way of overlapping them with their neighbors such that when you induce a current in here, you have this overlap such that current that gets induced here cancels out that's here. So you decouple those two coils by overlapping them with their neighbors. If there was no gap here that's opposite to the sign of the gap between this part and this part, right? If it was just two coils sitting side by side and there was no overlap, when you pulse current in one, it would induce a lot of current in the other one, right? So the neighboring coils would actually, if I pulse one over here, this one starts ringing because of the field that's generated from this one. So what you want to do is overlap them such that the field that's generated from this one, part of it induces current and part of it cancels current the other way. And so that gets rid of that mutual induction. So it's a clever way of packing a lot of coils into a space such that they're not all cross-talking to each other. And that way you can essentially just image what's underneath this coil, and you get 32 of those to add up all of the signals. You take your final picture with much higher signal to noise than otherwise. You can imagine you could put one big old coil here, and you would get a picture. This is the way it was done initially. The problem is that that big coil measures noise from the entire sample as opposed to a local location. And this also gets into what is noise in MRI. Random noise is generated from two major sources. One is anytime you have electronics, there is thermal noise in the electronics. So if I have a resistor and I put a voltmeter on both sides of the resistor, and I crank the gain on my voltmeter such that I have, say, a scope, and I look at it, you'll see random noise, right? And I did this as a physics undergrad. Then you take a cup of liquid nitrogen, you take the resistor, and you're looking at your noise like this. You drop it into the liquid nitrogen, and it cools the resistor down. And then you just watch the noise on the scope goes down. Right? There's less thermal noise because the amount of motion of the atoms basically in the resistor has gone down. Very similar, when we have one of these coils, and I put a patient in the MRI scanner, so I induce this magnetization in there in the person, a steady state. When I take my coil and I hook it up to a preamp and a scope, and I have a noise signal of a certain amplitude on it, and I'm just holding it in space. And now I put it up against the patient, the noise goes much higher. So the patient is the source of the noise. They are the resistive load on the scanner coupled through electricity and magnetism to generate a random signal in my coil. So I don't want to have a coil that's really large, and then when I put it up on a patient, I get this large volume of noise. Right? If I want to image a subfield, I don't want noise from the whole patient. I just want noise from my subfield that I'm imaging. Right? And that's why we all went down this pathway of multi-channel smaller coils for reception. Okay. So MRI is really interesting technology, and it's a beautiful set of equations. They're called block equations, which you can solve and drive to understand all the signals that are going to come out of your experiment for MRI. Itself, nuclear magnetic resonance is an entirely quantum mechanical process. It's an entirely quantum mechanical thing. And fundamentally, the reason that we get signal is because spin 1/2 particles, in our case, mostly protons, they can have two observable energy levels when they're bathed in a magnetic field. So if you just have a cup of water and you put it into a magnetic field, the protons in the water can, when you try and measure what state they're in, we'll find two possible answers. One is their spin is aligned with the magnetic field, and the other is their spin is aligned against the magnetic field. You cannot observe them in some position that they're like, 90 degrees of the magnetic field or something like that. This goes back to Stern-Gerlach experiment, which is used a lot in explaining quantum mechanics at a very elementary level. And read the Feynman lectures for this. It's a great explanation of what's weird about quantum mechanics. And if you have a beam of electrons, which are spin 1/2 particles, just like the protons spin 1/2 electrons, they also have spin 1/2. They will be in two conditions in the magnetic field, either up or down. If you fire those electrons, if you have a beam of electrons, you fire it through a magnetic field that has a gradient. They come through, if they're in the spin up state, they will hit the target in one location. Spin downstate, they'll hit the target in another location. And those are the only two possible observations. Okay? And that's spin. Turns out that if you have an ensemble of these spins, which is what we have in MRI, you can model the behavior of that ensemble with a thing called the magnetization vector. And it's like the expectation value of the spin energy of the proton. And it evolves in time, and it evolves after you inject RF into the sample. So it turns out that when you put a person or you put water into a large field, the protons are either up or they're down. And in the up state, right, they essentially have higher energy. They're pointed against the magnetic field direction. In the down state, they're pointed with the magnetic field direction, and they're in a slightly lower energy condition. Then obviously, what is the difference in energy between a proton in the down state and an up state? When you look at that difference, it depends on the magnetic field. And so if I am in a 1.5 Tesla magnetic field and I look at the difference in energy between a proton being in the up and down state, the difference in energy corresponds to a photon that has the frequency of 64 megahertz. Right? So it's just the classic H nu energy of a photon is the Planck's constant times nu, and that works out to be a photon with frequency. It's a pretty long photon, right? You can work out what the wavelength of that is, like slightly under a meter. So what happens in MRI is all of this goes towards or is explained in the ensemble, which is like a voxel. So I have a lot of protons in one voxel, and I ask the question, what happens with this voxel? You can write down the expectation value of this magnetization, and it's a simple set of equations. And so what we do is we quantify the polarization. There's a slight difference in the number of protons that are in the down state than an up state, slightly more in the lower energy state. Right? You can drive those into the higher energy state and they will fall back to equilibrium in the lower energy state. That's what looking at the magnetization vector allows us to do. So we have a static field, 1.5 Tesla, 3 Tesla, something like that. When we put our sample in there or our patient, what evolves over the course of a few seconds is a net magnetization in that patient. And this represents the surplus of protons in the lower energy state is this magnetization, so it's proportional to B naught. And then this is the magic. If we produce a radio frequency pulse at precisely the frequency that corresponds to the energy level to change a lower energy proton into a higher energy proton, if that difference is the radio frequency energy I put in there, I can modify this magnetization vector with that energy. And the way that modification is described with the Bloch equation is this flip angle. If we turn this on at a certain amplitude for a certain time, like a millisecond, we will tip the magnetization away from its equilibrium point, going in just the z direction, which is right along the magnetic field line. We can tip it away by an angle alpha. We call it either a tip angle or a flip angle, equally used. And that magnetization moves off this equilibrium point, right? That means there's a projection of magnetization down into the transverse plane. The transverse plane is that perpendicular to the direction of my magnetic. And we'll call that plane X and Y. The way in CT, remember we have the X and the Y direction is the perpendicular direction to the 4. And in MRI, same thing. Z is along the board, sort of the patient's lying it from their feet to their head, and X and Y correspond to left and right, and anterior and posterior. Correct. So now we have a projection of our magnetization in the XY plane. And it turns out because there's a Z field here and there's this projection, it will persist in this plane. This magnetization will persist in this plane. And that's what we're going to use to make the picture, right? It's that precession. And its magnitude and its phase are what we're going to pay attention to make the picture. If I turn an RF pulse on with a higher amplitude, right, such that this magnetization vector is rotating more quickly away from Z towards the transverse plane, I can set it so that I'll set this amplitude just right. Usually just tune this manually such that the magnetization vector flips entirely into the transverse plane. And that's called a 90-degree pulse. That gives us our biggest signal that we see. If over here, my alpha is, say, 10 degrees, it tips away. I still have a lot of magnetization in the Z direction, and I have a smaller amount in X and Y. And that would give me a small signal. This gives me my maximum signal possible. We're going to jump all the way to this one, where we double the amplitude of the RF that we're injecting into the transmit coil to twice the amplitude. The magnetization vector will go down to the XY plane, as it did over here, but then it'll just keep on going and it'll go down to negative M naught. So at this flip angle now is 180 degrees. So there's no magnetization in the XY plane. It's all pointed against the direction of the static magnetic field. We don't see any signal at this point. So what happens is this magnetization is now completely out of equilibrium. It's, it's sort of opposite. It flips the gradient of the equilibrium. And what will occur is it will, over the next few seconds, come back to this equilibrium point. And that's done by thermal jiggling of the phantom. The phantom. The protons in the patient. They're bouncing around, radiating towards each other, and they will, through thermal processes, they'll come back to an equilibrium standpoint. So if we do this alpha pulse, the tip angle is 90 degrees, so I get something in the transverse plane. As that is occurring, I am regrowing my magnetization in tip amplitude. Went down to, it's not negative, like 180 degree pulse, goes to 0. Then it climbs back up to equilibrium value. It's not going to go any higher than this equilibrium value. It will stay there forever, right? And this curve of recovery is called a T1 recovery curve. So if we start at 0 and it comes back to its baseline equilibrium value, we can characterize that curve with this equation. You can actually derive this, sort of principles. If you want to get a book by Schlichter or something like that for NMR, you can get this derivation. And it's a simple mono-exponential curve, just like beer heating up to the ambient temperature of the room, or coffee cooling down to the ambient temperature of the room. It just has that simple mono-exponential form. And the T1 constant used in that equation here is when, if you want to ask, well, what is that T1 time? It's when 63% of the magnetization is back towards equilibrium. And so that time is called T1. Whatever reason, anthropomorphic reason, it's that time is around for tissues, like for water. And so to image humans, that time could have been, you look at the universe and you say, oh man, if this coupling constant was slightly different, that time could have been like 5 minutes or it could have been 40 microseconds, neither of which we could have done in an image. But for some crazy accident, just great. It's about effect, right? So it's manageable. That we don't have to wait too long before we can do our next data acquisition. If I did a 90 and it just stayed there for 5 minutes, well, we'd have to come up with some other clever way to make a picture. What happens when the magnetization hits the transverse plane? It starts to precess, because this is a magnetization vector or magnetic vector, and there's a static field this way. It precesses around static field at the Larmor frequency. So it goes around here at 64 megahertz, right? That's equivalent to us, and then when we think about it, we put our receiver coil up to the patient. This magnetization is processing at 64 megahertz, and we receive signal from that. It radiates signal. What's actually happening is protons are flipping from the lower energy to the higher energy state, or vice versa. And we're measuring that is the true signal. But nobody I have ever seen has adequately described that such that you can relate it to the magnetization vector. Either go straight to the Bloch equation, or they stop at just the quantum explanation, and that's it. But I'd love to see a combination of those two. It'd be a great project. So what we see, if we look at the oscilloscope and we have our coil and it's on the right by the patient there, we're going to see the voltage do this. 64 megahertz radiation, that's the frequency, and then it decays away with time. So the magnetization in the transverse plane gets smaller with time. And as luck would have it, again, those times are kind of in the tens of milliseconds, 50 milliseconds, 100 milliseconds. So it's plenty of time for modern electronics to measure a signal, right? And so you measure this. The signal decays away more rapidly if the sample is large and there's slightly different magnetic field levels at different parts of the sample, or the patient for that matter. And so if on the left side of the patient, they're resonating at, a kilohertz different than the right side of the patient, when you mix the signal of those two sources, it decays away more quickly. So the higher the inhomogeneity of the person or the sample, the quicker this signal decays away. There is an underlying T2 relaxation curve that occurs if all of the protons in our sample are processing at exactly the same frequency. They will still decay, right? But the decay will be not as quick. So this is the actual T2 relaxation for a small sample that's absolutely uniform. And this is T2 star, what we actually observe have a practical large sample. You can recover the decay from this T2 star with a trick called a spin echo. This was very early on in MR, or nuclear magnetic resonance, that this was discovered and used. And that is, if I look at the magnetization vector in the transverse plane from different parts of my sample, and at one part, I'm processing at slightly lower frequency than the perfect on-resonance frequency. So I'm phase shifted compared to the perfect on-resonance point. I'm phase shifted back. This part of the sample is processing a little faster because the field's a little higher. So it leads in this precession. So it's going quicker, this is going slower, and you can see them this. Then if I use one of those 180-degree pulses at a specific time, let's say this time, I will take this point and it will flip over to here, and this one will flip over to there. This one will flip over to here, right? We're making a mirror image of that phase shift in the plane. And now this one, right, which was going more slowly, right? It was this guy up here going more slowly. It's still going more slowly, This one is going more quickly, and so they will, at a certain time, they'll come back together, right? And so that's called a spin echo, and that happens here. And so then you get a peak in the signal because all of those inhomogeneously resonating things have now come back into phase. That's called a spin echo. This leads us to our first pulse sequence, in which we provide a radio frequency pulse to the sample to knock these protons out of their equilibrium point. And we've modeled that as taking a magnetization vector and putting it down the transverse plane. That's the 90-degree nature of this pulse. We see a signal immediately as the magnetization vectors process around the static field, and we can measure that with our coil. It decays away with T2 star because different parts of the sample are resonating at slightly different frequencies. We then provide a similar pulse, but it has twice the amplitude, and it's a 180-degree pulse. This actually should be drawn such that it's higher. Anyway, this label is 180 degrees. And we apply that at TE divided by 2, and then at the time TE, we get a peak in an echo signal. And so this signal builds up and then decays away. And the envelope of that decay is T2 star. Right? So this we can use to make an image. And this was the pulse sequence, the original pulse sequence that was used a lot to make images because it was hard to make really good magnets, and it was hard to get the shim or the over the whole volume of a person to get all the frequencies the same, right? So this thing would decay away really quickly, and so you use the spin echo. Secondly, amplifiers were not great initially, and so you needed longer pulses here. And then gradient amplifiers, which we'll see next, is how we do our spatial encoding, used to switch quite slowly, and so you needed big time windows in order to switch those gradients on and off. And so instead of making an image with this signal right here, which is like a sensible thing to do, you couldn't really fit all of your magnetization management into this short period. So 180-degree pulse was used, and then you had a lot of time to do your management of magnetization and measure the spin echo. Nowadays, I would say 90% of imaging is done just on here, right? Because we have gradients that switch really fast. And so you can make or collect data much more rapidly. Like I have a pulse and I'm finished collecting data by here, and that's it. I can keep that over and over. 180-degree pulses, though, are quite useful for generating certain NMR properties that show up as contrast in images. So let's review the two contrast mechanisms we're going to lean on with MRI. One is differences in this longitudinal recovery, right, between different tissues. Remember when we look back at that, do I have a picture? Oh, I don't have a picture. The fat was very bright. And that is because we were imaging with a repetition time somewhere around here where the tissue that's, let's say this is water and this is fat, that has a short T1 and it shows up as a bright signal because it's already recovered by the time we go to make our next data collection. This is muscle tissue and it hasn't recovered. It's up to say 65%. And so when we apply the next pulse, we get a diminution in signal, and it's proportional to this T1 constant. So short T1 for some pulse sequences produces really bright signal. Long T1 is going to produce dark signal. In a similar way, if we look at the decay of the magnetization in the transverse plane, look at how quickly that magnetization vector decays away, we can have a long T2, and so the signal stays bright for a long time. Or a short T2 where the signal decays away and it's darker. So here are some, oh, look at that. I made ChatGPT make this last year, I guess, this table. So take it with a grain of salt, but I bet it's 90% correct. And it'll show tissue types and what the T1 value is. What the T1 value is at 1.5, 3 Tesla. And this is the extracellular volume fraction, the percent. And so it's these two that are of interest to us. So normal myocardium, T1 at 1.5 T is about a second. And then at 3 T, it jumps up to like 1.2 to 1.4 seconds. So at higher magnetic fields, you're going to have a longer T1, right, for myocardium. Same for edema. So here you have acute myocarditis producing swelling in the muscle, and so it's really watery tissue. And then that's about a second at 1.5, and it's up to 1.4 at 3. So these are all different types of tissue. And then the T2 recovery, normal myocardium is about 50 milliseconds, and it's about the same at 3T. T2 is not as sensitive to field strength as T1, and it's because of the nature of the interaction of the protons to generate both of these thermodynamic things. So is there any interesting? Well, you can look over these in the slides, but you've got about 50 milliseconds to get all of your, if you want to do imaging off the T2 curve, you got about 50 milliseconds to get. Okay, the next thing we're going to look at is gradients, although I did have a really good slide for where it went. Yes. What I want to do is, no, I thought I put it in here. Yeah, this slide's really good. So spin echo, that's making an image off of that spin echo that we just saw. This is making an image from the first signal right after the first RF pulse, or the gradient echo. And then this is a set of acquisition in which you shorten up the time between RF pulses such that it's like 10 milliseconds between each RF pulse, and you acquire data very, very quickly on that first RF pulse. And you can see they're remarkably different images you generate with those simple changes to MRI. You just change your pulse sequence and you can get all these different contrasts. Look how bright the contrast is for the inflowing blood here and here. Here, because it's a spin echo, basically the signal's gone. There is no signal because the spin echo signal, the blood that was going to generate our spin echo, it's gone. It's like out of the slide. So it doesn't produce any signal. That's pretty cool contrast mechanism. So this same person, all these different pulse sequences. And what, it became a cottage industry in MRI of labs and universities creating their own pulse sequences. And so that diagram that was essentially where the RF came in, this guy here, you have a 90-degree pulse, 180-degree pulse, a spin echo here. We're going to learn how to put in gradients and these pulses in different combinations to make different types of pictures. And so each manufacturer made a language for which you could make a diagram like this. I mean, that diagram was actually run on the scanner, right? So as you can imagine, this is just like a plotting function, right? So you can write your own pulse sequence API to basically then map it into whatever the Siemens thing is, whatever the Philips thing is, to make pulse sequences on there. All right, we'll start there on Wednesday. So any questions? I'll hang around for a little while. We can